Hey, John here. Let's talk about these things called AVL trees. So, what do we got? So, what are they? An AVL tree is a type of binary search tree. And we'll see that it is a binary search tree that we try to make look like this one in the middle here. All right? We try to keep it what we say balanced. All right? So, this one's balanced. What does an unbalanced tree look like? Well, these two on the left and right here are technically legal binary search trees. It is a tree, and every key on the left of every node is a key that's less than the one of its parent. So in a worst case, if you happen to insert all these nodes in order, in descending order, it's pre-sorted in descending order, and you just insert, right? 7, 6, 5, 4. You're going to end up with this, which is the same thing as a linked list because all the right children are empty. If they're sorted in ascending order and then inserted using the regular old binary search tree naive logic, number 1, then number 2, then number 3, because all the keys have to be greater than the previous node, have to be on the right child. All right? You end up with this worst case scenario where it takes order and time to find a node in here with a given key. This binary search tree in the middle here is balanced. It's optimal. Why? Because if this is just a binary search tree and we use the regular old naive insertion like we did here and here, and if the keys of the nodes to be inserted happen to be just coincidentally in the right order, that we insert, say, element 4 first, and then we do, say, a 6, and then we do a 7, and then we do a 2, and then we do a 5, and then we do a 3, and then we do a 1, it would build a tree that's perfectly balanced like this, all right? It builds a complete binary tree rather than something that's unbalanced, right? So this one's too far to the right, this one's too far to the left, this one's just right, okay? Let's take a quick peek at, the bigger universe of all possible types of trees, all right? Which we note here happens to be a type of graph. Well, that's a subject for a different discussion, okay? But what are all the types of trees? You got static trees, dynamic trees, game trees, search trees, heaps. Well, a binary search tree is a type of search tree, and an AVL tree is a type of binary search tree, okay? So AVL trees have to fit, these definitions that we might be associated with all these other types, all right? AVL trees are named after the discoverer/inventors of this thing. It turns out that they're kind of interesting because this is the first time that somebody proposed in literature that, here's a method to create a dynamically balanced tree and maintain it over the course of time. Now, it's a pretty simple algorithm. It's not perfect, but it is simple and it's pretty good. Now, as we'll see, the whole idea behind the AVL tree is that they maintain the idea of this balance condition of each of these subtrees within the greater tree. These balance conditions can only differ by at most 1. All right, so let's see what that's all about. So formally, we can then say that in order to be an AVL tree, it must conform to the following properties. Any subtree of any node can differ by at most 1 in their height. And then recursively, we have to say that every subtree, then, must also be an AVL tree. So let's see how that works. What does that mean? A difference in height of 1. So here's 5. How big is the subtree, the left subtree of this root node here? Well, the height of this tree is what? 2. How high is this subtree? 1. What's the difference? 2 minus 1 is 1. The difference is 1 or less. This is AVL. All right? What about this one? Well, the height of the subtree, the left subtree of 7, how big is that one? Well, that's a height of 2. And the height of the right subtree is 0. So this is a difference of 2. So this is not an AVL tree. Here's some more generic views of these things, and you can then reason this thing out again. All these here on the top are AVL. These ones down here are not AVL. So let's focus on the ones that are not and why. Why is this not an AVL tree? Well, if you look at the height of the left subtree of this root node, the height is 1. How big is the height of the tree on the right? If it's empty, we say the height is -1. Sometimes you can think about this. I tend to think about this not in the heights of the subtrees, which is kind of the formal definition. It also works if you just ask, what's the longest path length out to the left child of this node here? Well, that would be 2. What's the longest path length to the right? That's 0. So it's a difference of 2. Turns out that the difference in path lengths is the same as the difference in the subtree heights. Okay? Right? Subtree height of 1, subtree height of -1, the difference is 2, just like the path lengths, right? So let's look at this one here. What's the path length here is 1. Path length over here, the longest one we can clearly see is 1, 2, 3. The difference between 1 and 3 is 2. This is not AVL. What about this one? What do we got here? We got a 1, 2 for the path length there. We got a 1, 2, 3. Well, then why is this not AVL? Well, it's not AVL because this one, remember, the definition is recursive. It's not just about the root. It's about every single node in the whole tree. Well, what's the height of the left subtree of this one? It's -1. Or what's the path length to the furthest child out to the left is 0, right? What's the path length here is 2. Well, 0 versus 2, that's not AVL because this node here is not AVL. If you, again, do the whole thing using subtree heights, the subtree height of the left child of this node is -1. The subtree height of the right child of this node is 1. And the difference between those is also 2. So that's why this last one is not AVL. So what does this all boil down to? I hope it's somewhat intuitively obvious that if you have a tree that is already compliant with the rules of being an AVL tree, the only thing you have to concern yourself with over the course of time, I mean, it's a subclass of binary trees, are those operations that cause the tree to change its shape. Any other operation that you want to do to a binary tree is fine on an AVL tree. In other words, the searching. Given a binary tree, and an AVL tree is a binary tree, how do you search? You start at the root, you go left and right based on the relative size of the key you're looking for. Searching is fine, okay? But if you want to insert or delete into a tree that's an AVL tree, we have to then consider if we have caused it to become out of balance. As we just saw, the idea of its being balanced or not, we use something that they officially call the balance factor. And that is the height of the left tree minus the height of the right tree. Or, as I already pointed out, you could say the length of the path to the furthest child minus the length of the path to the furthest child on both the left and right subtrees. Okay? The balance factor of any node in the AVL tree must be no greater than 1 in difference, right? So therefore, it could be -1 or +1. And an evenly balanced node would have a difference of 0, right? And one node with 2 children and no other nodes in an entire tree would have a balance factor of 0 because both the left and right have the same size. And x minus x is 0, okay? That's what happens in order to maintain these rules. Now, as we'll see, we do allow the balance factor to become out of whack temporarily when we're manipulating the tree. What we're going to do when we look at what does it mean to insert a new node into an AVL tree, we're going to just use the regular old binary tree insertion. And then, when we're done with that, we're going to check to see if we've made the tree out of balance in doing so. And because we have only inserted one and only one node, we can at most change the height of any subtree by 1. So, after we do the initial insertion into any tree, we can see that the range of the balance factor could be as far as -2 to +2. Now, as I just said, once we're done inserting, we have to check to make sure everything's okay. And if it's not, because some node has gone out of whack, we have to fix it. And we use what we call a rotation to do that repair. And we have these single rotations and double rotations. And we're going to see that every one of these is really a variation of the same theme. So let's first define what a rotation is, okay? What we're going to do is we're going to change the structure of this tree without changing the order of the keys of these elements, okay? Now, these are just arbitrarily labeled. Clearly, these are not sorted. the letters in these trees are not the keys of these nodes. They're there just for reference, okay? Maybe this slide could be improved. Anyway, I apologize for that. So what we're going to do in a rotation is we're going to reverse the relative height of two nodes. Okay, they say in the literature that what we're doing is we're changing the heights of nodes, or the position vertically, I should say, versus changing them horizontally. Okay, right? Because P and Q, P is left of Q, it still is, right? We're going to keep that the same, but we're going to, change around the heights. So what do we got here? If I'm going to say do a right rotation on Q, what does that mean? It means that what we're going to do is we're going to change the pointer here, and we're going to change this pointer here. Look at the difference here. So a right rotation with Q, we're going to say what? We're going to change the pointer to the right child of P is going to point to Q, which is going to achieve this relationship here. And the left pointer out of Q is going to adopt the right child of P. That's all you got to do. You got to swap those two pointers. That's why B goes from being the right child of P to becoming the left child of Q over here. Okay? Now, this is a symmetric operation, easily reversed. Once you've converted a tree from here to here using a right rotation, a left rotation, which is the exact same sort of thing, we'll see a more detailed view of that in a minute, we'll flip it back again. So this is a reversible operation. Now let's look a little bit closer at these rotations and the movement of these pointers, all right? First of all, let's look at this diagram as a whole. You see the way this circle is drawn here? What we're showing here is the symmetry, right? If I'm going to do a right rotation to change a tree from this to this over here, I can then apply a left rotation to go back to where I started, okay? So let's zoom in a little bit here on the right rotation, which is the same sort of thing we're just looking at. So what do we got? Now this is labeled as root and pivot. This does not necessarily, as we'll see in the examples that follow here, this is not necessarily the root of the entire tree. This is the root of a sub-tree where we're going to apply a rotation. Okay, so be careful. This labeling may not be optimal here. Don't walk away with the impression that this can only happen at the root of the whole tree. This is the root of a subtree. So what do we do? Well, like I said, the left child of the subtree root no longer points to where it does. It adopts the right child of the thing that I'm pivoting around when I'm doing a right rotation. So this pointer here is changed, as you can see, to point down to the 4. Then the pointer from 3 down here to the 4 is going to be changed to point up to what was the root here, the 5, right? So that's shown here. Now, normally you don't draw a tree this way. It's easier to recognize it when you do this. So the difference between this drawing here and this one here is this: we vertically, visually moved this one down where it belongs, okay? So all we've done is change two pointers in order to perform a right rotation. That changes the balance from being left heavy in this diagram here to being right heavy in this diagram here. Now, observe also that this tree here is AVL, and the tree over here is also AVL. So if this is the only thing you have in your entire tree, my point is, you normally wouldn't do a rotation on these, but this is just a close-up sub-view of what could be part of a larger tree, okay? It boils this rotation concept down to its essence, all right? So what happens when we do a left rotation? It's the exact mirror image. Look what's happening here. We're now starting with this, which is where we ended up above here, right? We want to do a left rotation with 3 here being the root. What do? Well, again, in this case, it's the mirror image. So you're going to take the right child of 3 and repoint it to the right child's left child, and you end up with a pointer that looks like this, okay? And the pivot location here, what was the right child of the root here, we're going to adjust its left pointer to point up to where the root was. So that's shown here, okay? And again, we don't normally draw trees that look like this because they don't look so good, and we can just move this visually down and see that it is still a binary tree, and we end up back where we started, okay? So with that in mind, let's generalize this. What is the situation then? When do you apply these, and how do they work? We have 4 situations that require rotations when we're trying to rebalance a tree. Let's look and see what they are. They're called LLLR, rather down here, RR and RL. What does this all mean, right? Well, we call this a left-left, because if this is the tree or the subtree that you want to rebalance, in the starting condition of the thing, we say that Z is left heavy because it's got a max path length of 2 over here and 0 over there. That's out of balance. And it is the nature of this thing being out of balance that it is left heavy, and its child subtree over here is also left heavy. So that's what we call an LL. And to fix it, we do a single right rotation. Okay? We signify that by saying R sub Z over here, right? So what are we going to do? We're going to do a right rotation. We're going to restructure this tree to bring it back into balance. You adjust the pointers as you saw on the table above, and you end up with this. Okay? Right? Because in this case, the right child of Y is empty. So when Z over here adopts that right child that we saw above, it's adopting an empty tree. Z on the right was empty before, so when that's all done, Z becomes a leaf node, as you see over here. Now, Y used to have an empty tree here, and we replace that with a pointer that points up to what used to be its parent. And that's why Z becomes the child of Y here. That's how we get this thing balanced. Now, the mirror image for a right, obviously, right heavy subtree. We fix that one by doing a left rotation, just like we saw above. Z is going to become the left child of Y in this scenario. Okay? What's this LRRL stuff? Well, if you have what a golfer might call a dog leg here, okay? This is left heavy. Z is left heavy. And Y is right heavy. So this is an LR. How do you fix that? Well, with this one, we have to do 2 rotations. I like to think of this as a Kobayashi Maru type thing for you Star Trek fans. We can't really fix this. So what do? We make it into something else that we can fix. So what are we going to do? We're going to do a left rotation around Y. And once we've done that, we'll see it's going to change the X to here, the Y will go over there, and you're going to have ZYX. You're going to have this problem up here. And once that's done, you just fix it like you did here. Okay? And how you do that? You do a right rotation around Z, bang, you end up with this. Same thing if you got a right-left. Mirror image. Can't fix it. Change it to something we can fix by right rotating this. You end up with that. You then left it on Z. You end up with this. So in those cases when your tree is out of balance by more than 1, what do? We execute this algorithm right here. If it's right heavy and the subtree on the right is left heavy, we need to do an RL set of rotations. So we right rotate the subtree, and we left rotate it at the root. If we're right heavy and the subtree is right heavy, we do the RR rotation, which means you just do a single left. Otherwise, you do the other two cases. It's not right heavy, and by definition, this means that the tree balance is out of whack by more than one, right? You don't even do this at all unless you're out of balance, right? So if it's not right heavy, it must be therefore left heavy, given the definition of the situation. And if it is left heavy and the subtree is right heavy, we end up with a left right, and then we do the left and the right. Otherwise, we've got a left heavy tree that's also got a left heavy subtree. We do a single right rotation to fix it. So this is how you deal with those four cases, okay? So let's now look at what happens when we do an insertion. All right, given an AVL tree, and you can see this is AVL because you can calculate the balance factors of all these things and see that that is in fact the case, right? We'll do one. I'm not going to do a lot of these, but let's say I want to know the balance factor of 3. By definition, every and all leaf nodes in any tree are balanced because they have no left subtree and they have no right tree, no matter what notation you use to represent the heights of those trees or the length of those paths, they are equal. Therefore, the balance factor of all leaf nodes is 0. They're always in balance, okay? What's the balance factor of 4 here? Well, if you use the path method, it's 1 minus 0. It's 1. If you use the height of the subtree method, the height of this tree is 0. The height of this tree over here is negative 1. 0 minus negative 1 is 1. Therefore, it's 1. All right? So both of those techniques work. What's the balance factor of 2? Path method. 1 minus 2. This is right heavy, okay? But its balance factor is negative 1. It's okay. It satisfies the rules of AVL. What about the 8? We got a length of 1 here, length of 0. That's in balance. 5. Well, the length of this is 1, 2, 3. The path length, maximum path length on the right is 1, 2. That's within 1. So this is an AVL tree, all right? I'll leave the rest of these verifying that they're AVL trees in these examples as a test to the viewer. Okay, what if we want to insert a new node into that tree? We want to insert a 6, okay? All right, where does it go? Well, 6 is greater than 5, less than 8, less than 7. It becomes the left child of 7. And the regular old naive binary search tree insert rule. You end up with the tree that looks like this. Okay, there's our new node. What do we do? Well, when you do an insertion into an AVL tree, what you do is you start at the inserted node and you just walk up to the root. You don't have to check everything after you do the insert. You only have to check the path from the inserted node up to the root. The only thing that could have become out of balance as a result of this insertion, okay? So what do? We know the inserted node is a leaf. Don't even have to ask. You go to the parent. What's up with it? In this particular case, we got a 1 minus 0. He's okay. You go to the parent. What do we got here? We got a 2 versus 0. What is the balance factor of that? It's 2. It's the length of this path minus the length of the path on the right. Or it's the height of this subtree minus the height of the subtree on the right. Either way, you get 2. What do you do to fix this thing? Well, he's out of balance and it's left. How do you fix that? You do a single right rotation. Now notice this is a more reasonable example here because you got a whole tree involved. If you block this out in your mind, you can see that the 8 goes down here, the 7 adopts the 8, then the 7 comes up here, right? The 8 adopts the right subtree of 7, which is empty, and it becomes a leaf node. You end up with this situation right here. But also notice that the parent of 8 used to point to 8 here. When we're done with this rotation, there's this one more link that we need to update. 7 has to replace 8 in the tree as a whole. So there could be 3 pointers that you need to update when you do a right rotation or when you do a left rotation. Okay? So keep that in mind. All right, so let's say we want to insert 1, 2, 3, 4, 5, 6, 7 into an AVL tree. And we saw this before in a BST tree. You end up with this really right-heavy tree when you're done. It looks like a singly linked list. But in an AVL tree, we rebalance as we go. What do we end up with? Start with an empty tree, insert a 1. You got a single node in the tree. It becomes the root. Done. And then do a 2. 2 is greater than 1. It has to become the right child of 1. Put it in there. Okay, let's check to see if it's in balance. Don't have to check the leaf. Go to the parent. height of this subtree here is -1. The height of this subtree here is 0. -1 minus 0 is -1. That is a balanced AVL tree. Let's insert a 3 now. Well, the 3 has to go over here. We already saw when you have 3 in a row like that, it's right heavy. So we're going to have to do a left rotation to fix it. You reconnect the links, and you end up with a tree that looks like this. Okay? What happens when we insert a 4? We insert it down here, and we don't have to do anything because this tree is imbalanced. Just because you got 3 in a row doesn't mean you have a problem. Right? Because the only reason you have a problem when there's 3 in a row is when you got 3 in a row with no left subtree. In this scenario here, if we look at the total subtree height of this tree over here, the height of that is 0. What's the subtree height of this one over here? It's 1. 0 minus 1, -1. It satisfies the AVL rules. If you want to think of it in terms of path length, you got a path length of 1 here and a path length of 2 here. 1 minus 2, -1. Same thing. This satisfies the AVL tree. What happens then when we insert a 5? Well, we look over here, what happens? 5 is greater than 2, greater than 3, greater than 4, and it goes down here. Now we got a problem. Because now we have the 3 in a row, and none of them have left subtree, so the imbalance is out of whack here, right? So in order to fix the 3 in a row to the right, you need to do that's an RR situation. We got to do a single rotation to the left. You end up with this over here. Okay, what happens when we then want to insert a 6? Well, the 6 has to go over here, and we have another imbalanced situation. So I'm going to ask you to visualize a little bit more in your head this time. With the 6 down here, would that be an AVL tree? And the answer is no. Why? We know the new 6 is a leaf, it's imbalanced. The 3 is imbalanced. The 4, or the 1 over here rather, is balanced, okay? Because they're leaves, they're always good, right? So in the path length scenario, what do you got? You got a path length of 1 here to the 6 that's not drawn down here versus 0. That differs by only 1. So 5, the balance factor on 5 is good. What about this one? It's got a maximum path length to the left of 1. Maximum path length to the right would be 2. That's satisfied. Okay? What about this one? It would have a maximum path length to the left of 1. Maximum path length to the right with the 6 in there would be 1, 2, 3. Now we got a problem. So this tree is in balance everywhere except at the root node. And what kind of imbalance would that be? Well, that's 2 would be right heavy, and the right subtree with a 6 down here would also be a right heavy. So we have to do a single left rotation with 2 as the root, and we end up with this. Okay? If we then insert a 7, we end up with the tree over here, and it is in balance because, right, 7 is greater than 3, greater than 5, greater than 6, but way down here. So this is about as out of whack as a tree can be and still be satisfying the AVL rules, okay? You'll notice this isn't perfect. You could do better by hand by just going through and rebalancing these trees because it's just 1, 2, 3, 4, 5, 6, 7. If you really wanted to, you could create a perfect, balanced, complete tree with these nodes. And as I said before, AVL is not perfect, and this is an example of that imperfection because it tolerates this as acceptable. All right? AVL it strives to achieve as good as it can based on the simplest algorithm here, okay? How come this is satisfying the rules, right? Well, 7's AVL, 6 is path length style, 0 versus 1, that's good. When I got 1 versus 2, that's good. What do we got for the 3 here? Well, let's go to the subtree here first. 1 and 0, they're only differing by 1, so 2 is good. 3 has got a 2, and he's got a 1, 2, 3. Those are also only differing by 1. So this tree here, even though an imperfect, balanced tree, in other words, we could do better, does satisfy the AVL rules, and these are all AVL trees, okay? Closer look at what happens during the insertion process and what has to happen is shown on this slide here, okay? So we got nothing, we insert the 1, we insert the 2, we end up with this. You'll notice the insertion of these elements is in a little bit different order here. Then what happens? We got a 3. So we end up with 1, 2, 3, and it's starting to become a linked list. This is a right heavy imbalance with the root of the top node here. To fix it, we do a single left rotation. We end up with this, okay? We then insert the 4. So far, this matches what we were doing before, right? And the 5. So you end up with a tree that's out of balance, right? So this is right heavy. You fix it by doing a single rotation to the left. With 3 as the root, you end up with this right here. Then what happens? We're going to insert a 0 into this tree here. 0 is less than 2 is less than 1. Therefore, it would become a left child of 1. And you end up with this tree over here. And you don't have to fix it because this is still maintaining the balance factor requirements for the AVL tree. What's next? We put a 7 in there. Well, 7's greater than 2, greater than 4, greater than 5. It goes way down here. Is that an AVL tree? Yes, it is. Because the maximum path length left here is 2. Maximum path length to the right is 3. That's good. What about this node here? 1 versus 2, it's good. 0 versus 1, it's good. 1 versus 0, that one's good. So this is fine. As you can see, sometimes you do an insertion, you don't have to rebalance the tree at all. What happens then if we decide to insert a 6 here, right? The last one after the 7, we're going to insert a 6. Well, 6 is what? Greater than 2, greater than 4, greater than 5, less than 7. So the 6 has to go to the left of 7. It's 7's left child. We end up with a tree that looks like this right here. We got one of these dog leg left type of things here, right? So we're not in balance anymore. What do you do to fix that? We have a right left. Okay, as the note says right here. How do you fix that? Change it into 3 in a row. Okay, change it into a right, and then you fix the right by doing a left rotation on the root that was imbalanced to begin with, right? And you end up with a tree that looks like this, which is an AVL tree. All right, now this slide here goes to show you the heights of these subtrees in a closer view of what happens over the course of time. We don't need to go over more examples of the same old thing. Just note that the notation used in this particular slide is based on the height of the subtree on the left and right sides of this node here. On an empty tree, we say the height is -1. And this height of this tree is simply 1, right? So the height of the left subtree of this node here with a 40 as a key is -1. The height of this tree over here is 0. The height of its subtrees are both -1s, right? And you do the math on here, and you can clearly see that -1 minus 1 is -2. This fails to meet the AVL requirements, and you fix it with a right rotation because it's obviously right heavy, okay? Here's the same thing, adding a few more nodes. Right, 20 and then 40, and then we do a 60. We have to rebalance that, and we end up with a tree that looks like this. Then we add a 10. 10 is less than 40, less than 20, so it becomes a left child of 20, right? And we then add a 15. At the point that we had the 15, right, it's less than 40, less than 20, greater than 10, so it becomes a right child of 10. We end up with a tree that looks like this. You can clearly see one of these dog leg things sitting in here, so that's a left-right, okay? And how do we do that? We go left on this node here. We go left on the 10 to change it into a left, and then we fix the left by doing a right rotation with the root at 20, and we end up with this. Now, continuing this flow, what happens if we then add a 12? All right, we left off right here, right? Where does the 12 go? Well, it's to the left of 40, left at 15, right of 10. So it would go over here. We end up with a tree that looks like this. Now, what's the balance factor here? Well, what's the height of this subtree? It's 2, right? What's the height of the subtree here? 0. So you can see the 2 and the 0. So the balance factor here is 2 minus 0, which is 2, and this is out of whack. This is not a valid AVL tree. How do you fix this? Well, it's left heavy. We need to do a single right rotation at 40 to fix it. And I can clearly see that this slide is wrong. Well, that is a wrong example. I apologize for that. And unfortunately, I don't have time to fix it. Normally, I'd stop the video here and fix this thing, but these aren't my slides. Whoops. Let's look at this using an animated AVL tree demonstration application and show you what's supposed to happen after this point as it evolves into what it's supposed to become, which is not this, okay? All right, so if you do a Google search on AVL tree animation, you're going to find a couple of these things floating around out there. Okay, let me scroll this down. There you go. Now you can see what we wanted to insert that I didn't quite get right in the slides. And we can use this tool, and this is kind of neat. It'll do these little animations. So what do? You type in the node numbers here. 20 is the key of the first item. You hit insert. Okay, that becomes the root. There's the 20. Okay, now what do you have? We do the 40. And we hit insert and watch the animation. It'll say, okay, it's supposed to be the right child of what was the root. And you saw those rings moving around in here, right? So what that did is it said, look, I know that 40 is greater than 20, so I'm going to insert it down here as the right child of 20. And when I'm done, I'm going to traverse back to the root, checking my balance factor to make sure everything's okay. And you'll see in the animation, here, let me slow it down really nice and slow. That it will restructure the tree by doing the rotations if necessary. And of course, it did not need to do one there. If we do a 60 here, it's going to need to rebalance the tree, right? Because I got a 20 and I'm putting in a 60. So 60 is greater than 20. It's greater than 40. It's going to go down here and we're going to end up with a right heavy tree. Okay, so there it is. It's doing the binary search. Finds out it needs to go down there. It goes to the parent. That's okay. Goes up here. Uh-oh, it's not okay. So what is it going to do? It's going to do the left rotation to fix the tree. All right? So now what happens? I'm going to do the 10. Where's that one going to go? Well, 10 is less than 40, less than 20. It's going to go over here. And once it does that, it will be in balance. We don't have to rebalance it, right? So there's doing a binary search. It decides to put it down there, and now it's going to check the balance factor up back to the root from the inserted node and find out it's okay. Here's our 15. It should become the right child there. Now it's going to check the balance factor and rebalance when it needs to. All right, and continue on to the root to see if anything else needs rebalancing. Okay? All right, now... Here's where my slides went awry. We're going to put a 12. Where is it supposed to go? It's less than 40, less than 15, greater than 10. It needs to go down here. Okay? And then we need to rebalance the tree. So let's see what it's supposed to do. Greater than 10. Insert the thing. Check the balance. That's good. Go up here. That's good. Go up here. Not so good. What's he going to do? He's left heavy, so he does a single right rotation. This is what the slide should have said after we inserted the 12. Look what we got here. We see the 15, the 10, the 12 on the left here. And we see the 40, 20, and the 60. My slide does not have the 15 in the... This is just broken. I apologize. So for this example, go find one of these animation systems and look at what happens in there, okay? What happened? Let's finish it off. Where does the 11 go? Well, 11's less than 15. It's greater than 10. And it's less than 12, so it's going to go down here. And then we're going to see that 10 is going to be out of imbalance, and it's going to have to fix it, right? Less than 15, greater than 10, less than 12, insert left child. He's balanced, but this one here is not in balance. So it'll do a left rotation. Continue on up to the root to make sure everything else is okay. We end up with a nice, clean, complete binary tree. Not quite what this example. I'm going to scroll to the next page and pretend we didn't see that. Okay. So then what happens? We've got, what do we got? A whole different example of what's happening here. I'm going to leave this one as a task to the viewer to see if there's any errors in this slide. Okay. But this is really just more of the same. Okay. And in more scenarios as the tree grows to larger and larger shape, but it's really just more of the same. So let's move on to what it means to delete nodes out of a tree. So just like the binary search tree, we're going to just delete it using the regular BST deletion. And then when we're done, what we're going to do is we're going to check the tree if it has gone out of balance. And as we know from deleting nodes on a binary search trees in the past, we have 3 scenarios. So in the case when a node is deleted that has no children, what you do after having deleted it, you just simply traverse the path from the deleted node back up to the root of the tree, checking the balance factor as you go. Because the tree has otherwise not been restructured anywhere else, you know that if anything has gotten a balance factor that no longer satisfies the AVL tree rules, it would be one of the nodes along the path to the root from that deleted child. Same thing happens if you delete a node that has a single child. Because remember, in the binary search tree, when you delete a node that has a single child, that single child just simply moves up to take the place of the deleted node. So what you've done is you've only changed the height of the tree at the position where that node had been deleted. The same thing when you have no children, right? So therefore, you just traverse the path up to the root from the point where the deleted node was removed. You don't have to go back down to the leaves or anything like that. You just go from the deleted node back to the root in these 2 scenarios here. Things are a little bit more complicated, just as they were to delete a node that had 2 children, right? You're kind of dealing with the predecessor and the successor, depending on how you do the deletion, right? You can choose to always move the successor over or the predecessor over. We talked about that when we were talking about binary search trees, okay? So what happens is the node that's deleted that has 2 children, when you move the successor over, the rule is you only have to verify the balance factor of those nodes that are from that successor leaf that you relocate during the delete operation up to the root. Okay, so this one's weird, right? You don't traverse the path from the deleted node up to the root. You traverse the path from its successor up to the root, the one that you moved, okay? So here's an example, and we're going to use a little bit different notation this time. The way this tree is labeled here, we're looking at the path lengths rather than the total height of the subtrees. The math works the same either way, all right, as I've been saying all along. We also show the balance factor in these nodes. I guess this slide deck has a little bit to be desired. A little more consistency and remove that other error would be a good idea. All right, so given an AVL tree, all right, what if we want to delete node 15 here with a key of the 15 right there, that one, okay? What do? When you get rid of it, and in order to delete it, what are you doing here? You're going to move the 17 up to, right? This is the successor. Well, this example uses the successor logic rather than the predecessor, right? You can use it either way. So what are you going to do? You're going to take this one out. You're going to move the 17 up here, okay? In order to deal with this, we have to look at the path to the root from where this one went away, so we're going to check from here at that point, right? And we're going to see the balance factor here is -1 because you got 0 here and 1 here. Again, these are the path lengths this time. And the balance factor here is -1 because you got 1 versus 2. The balance factor here is 3 and 3. That's imbalance. And we don't even need to look over here because this subtree didn't change in any way. Okay? So we know we're satisfied. What happens if we then want to delete a 12? We want to delete this node right here. What happens? Well, the balance factor of its parent just went on a whack. Like as I leaped forward here kind of quick, right? Remember, we're deleting a leaf node. And the rule in the binary search tree is you just simply remove it and null that link out. And in the 3 cases on the previous slide up here, we're dealing with this one here. So we're going to go from the deleted node to the root, and that's what we're going to check the balance factors there. So 12 disappears. We go up to its parent, and we say, okay, check this guy's balance. Well, you got 2 here in a path length, and you got 0 on the left, and its difference is 2, or -2 for the balance factor, and things are out of whack. We need to rebalance. We got a right heavy. So we're going to do a single left rotation with 17 as the root, and we end up with this. Okay? Now after that rotation, we can continue up here and keep checking. Because this would have changed, right? It used to have a length of 3, now it has a length of 2. And because this thing only reduced it by 1, it went from 3.3 to 3.2. This difference, the balance factor here is 1, and we're done, and it satisfies the AVL rules. So here's a more complicated example here, right? What are we going to do? Given that this is an AVL tree and I want to remove node 4, which is right there, what do? We remove the 4. And if you look at this, what would have happened here? Well, this tree here used to have a 2 and a 1 for the path lengths. It used to be happy. You remove the 4, and now it's got a 2 versus 0. It needs to fix that by doing a right rotation, where 3 is the root. Okay? So, with 4 gone, you end up with this. You need to fix this, and he's double left. So he's going to rotate this one around to the right. We end up with this. Okay? Now we go up to the root and check again. Because just because we fix the subtree, we're not done. We got to keep going all the way to the root. That's why this example's here. So this one's done. He's happy. We move up to here. What do we got now? We got a 2 for the path length here, and we got a 1, 2, 3, 4. This is obviously the longest one. 2 versus 4 is a problem, right? So now we need to fix this. What do we got? Well, this turns out to be what? He's right heavy. And this subtree down here is what? Is it left heavy or right heavy? Well, it's obviously right heavy because the left subtree, the full path length here is 2. The longest path over here is 1, 2, 3. Now, this whole thing here is AVL because its path is 2 versus 3. But it's right heavy. And the rule to fix this one is that this one's right heavy and its subtree is right heavy. What do? We do a single left rotation with 5 as the root. Okay? And once we've done that, we end up with this over here. And to do that, what do? Right? We got to swap around these pointers. Because 5 adopts the left child of 8 in order to do this left rotation here, right? So when 5 adopts the left child, 5's right child is the 7, and this 6 over here. So this thing moves over to be the right child of 5. And then when that's gone, 8 has to relink up to 5 up here. 5 becomes the left child of 8. That's why the tree ends up looking like this. And this one then is going to be, by definition, AVL, because we would have traced up to the root all the things that need to be fixed to simply delete the one element. Okay? So to fix it, we had to do 2 sets of rotations while we traverse from the deleted node 4 up into the root to check the balance factor on all the way. All right, so what are the pros and cons of these things? Well, obviously, the AVL tree is better than just a binary search tree if you're going to be inserting and deleting nodes over the course of time, especially if they're inserted in sorted ascending or descending order. It'll attempt to maintain a balanced tree. Okay, it's not perfectly balanced, but it's very close. It's certainly better than just a binary search tree because it won't allow it to get out of balance by more than some amount and keeps you closer to that optimal log n time to do the searching to find nodes in the tree. What else? The height balancing adds no more than a constant factor to the speed of the insert and the delete, right? And in many cases, you don't do anything once you've reassessed that balance factor, okay? So what's bad about it? Well, we need more space because we have to store all those height fields to calculate the balance factors, right? And the rebalancing does take time. I mean, if you have a binary search tree and you know that the order in which the elements are added are going to be in a very random order that just so happens to maintain the balance anyway, and, if you're in a situation where you can't afford to perform all the rebalancing every single time you do an insert or a delete, then maybe you can just use a regular old binary search tree. And you can get away with it. But this is very dependent on the data in the order in which your data is inserted and deleted, as you have seen, right? Now we throw in a bullet down here and we make the observation that a lot of large searches these days are done using database systems where all the data is on the disk anyway. And they use different kinds of structures, like a B tree or some other kind of a tree, or an index of some sort, is the point. And AVL trees aren't really useful in that particular situation. All right. Now, I'll also observe that while this is true for most, and this is always the fallacy everybody gets caught up in, well, most of the time it's this. The question is it all of the time? And the answer is no. Sometimes. When it's real important, those sometimes situations can be critically important. Okay? So you can't just blindly say, oh, we don't need AVL trees because most of the time we don't need them. Well, I don't know about you, but most of the time is not good enough for me. Would you like to be alive most of the time or all of the time? I'm going to go with all of the time, right? Like I said, there are situations where it's just not acceptable to be right most of the time. Sometimes you have to be right all of the time. And that's why we need to be cognizant of what's going on with these trees. I'll give you one example where I know you have to not use a database-like system on disk if you want to win, okay? If you want to trade stock, you want to keep track of all of the values of the financial instruments in the market and make decisions quickly, because opportunities are there for a short period of time. The first person to find an opportunity that's caused by the changing pricing of various instruments in the markets, only the first person gets to win that game. It's like the game of spoons. Whoever finds it first and can act upon it wins. They keep all the money. Everyone else loses. I absolutely guarantee that the winners do not use database systems to make their investment choices. They buy machines that have enormous amounts of memory, and they handcraft data structures that match perfectly the situation that they need to deal with, so that they find the answers first. And that is an example where your business will either win or lose based on the choice of whether you take a few minutes to think it out and pick the right kind of index for some data versus, most of the time this is fine. Well, most of the time is not all of the time when you're investing your money in the stock market. I don't know about you, but I like to win, especially if money's at stake. I'd rather gain over time than lose. All right? So, this is a true statement, but it doesn't mean that we just throw this away in all cases. All right? Now, here's a couple of useful links at the end of this slide deck here. I'll also throw a note into my visualization. I think actually the one that I showed might be this one right here. There's a bunch of these, like I said, on the web. And you can use those to overcome the strangeness if you find a slide deck like mine that has a typo in it, okay? And you can verify that they're correct. Here's a few other acknowledgments of where some of the data came from for this slide deck. Again, this slide deck, look in the notes under this video in the description. I'll put a link to the course website. You can get the slide deck for yourself. Thanks for watching.